Okay, good evening, everybody, and welcome to another organic chemistry session. I also would like to welcome you back from your long holiday weekend. I hope you had a very restful weekend, right? Okay. Today we are going to start our discussion on the chemistry of ethers and epoxides, which is taken from chapter 18 of your book. Specifically, we are going to discuss nomenclature, synthesis, and reactions of epoxide and ethers. And at the end of our discussion today, we will briefly discuss a fairly unique chemical reaction we refer to as Claisen rearrangement. This is a reaction that involves ethers. Okay, but before we get the session started, let me just make a few announcements. Tomorrow, that is February 20, that is Wednesday, February 20, at 8 p.m., there will be an online session. And for the online session tomorrow at 8 p.m., we are going to use the end of chapter 18 questions in our further session. I also want to remind you that the homework assignment for this week, that is the our end of chapter 18 questions, and that is due on Monday, February 25, okay, at 11 p.m. Okay. Okay, now, on the next slide, we show you what we call, of course, the learning outcome objectives, which means that upon completion of this chapter, you should be able to perform all of the different concepts and topics that are shown on this list. In other words, you should be able to write the IUPAC names for ethers, write the structures of ethers when given the IUPAC names. Also, you should be able to write the reagent that will convert alcohols and alkenes into ethers and epoxides. So I will urge you to come back to this slide just to make sure that you understand all of the concepts here. Now, also, before we get started today, I am assuming that all of you have had the opportunity to watch the webcast of the previous chapter 18 lectures. Because today what we are going to do is essentially go through our problems. Of course, while we go through these problems, I will also introduce some of the concepts to you for the benefit of those of you who may want some refresher. Okay. Okay, for this purpose, I will be using the end of chapter 18 questions. Okay, and then whatever we finish today, wherever we are, as far as we can go today, then tomorrow we will take off from there for the online session. Okay. Okay, so at this point, Lorenzo, can you go ahead and read this for us?
Give IUPAC names to the following compounds. Be sure to specify stereochemistry.
Okay, thank you. Now, what they want us to do here, to give the IUPAC name for this compound here, this compound and this compound, you can see, as you can see here, if you take a look at this molecule here, how many classes of compounds do you have here? How many in this molecule? How many classes of compounds? Okay, what class of compound is this? This here. This here, right here. Oh, it's black? Okay. It is red on my... Okay. Sorry. So I need to check that projector. Okay, it is red on my screen. Okay. Anyway, so what we have here, let me write it for you. Let me go ahead and write it. So what we have here, we have this. Then we have this here. Okay, so that is the molecule that you have here. Now, how many classes of compounds do you have in this molecule? Two, okay? What are the different classes of compounds? Alcohols and ether. Very good. So this part of the molecule, this is your alcohol function, right? And this part here is your ether function, which is to say that if we ask you what is an ether, what is an ether? An ether will be what? Oxygen attached to two carbon atoms, exactly. So anytime you have an oxygen attached to two carbon atoms, then you have an ether. Okay. In this case, they want us to give the name of this compound. So let us go ahead and give the name of this compound. Now, whenever you have an ether functionality in a molecule, and you also have another class of compound, for example, an alcohol, the alcohol will take precedence. In other words, the preference will go to the alcohol. So in this case, we are going to name this molecule as an alcohol, in which the ether will become a substituent. Now to do that, if you have this here, this methoxy group will become a substituent. So how do you then name it as a substituent? Of course, I've already given out the name as a methoxy group. How do you derive that? So you say this is a methoxy group. Now supposing we have this. Supposing we have that, what kind of group is that? What kind of group would this be? A toxic group, okay? This would be an etoxic group. So in other words, to name an ether as a substituent, what you do, the name is derived from the name of the corresponding alkane. In this case, the corresponding alkane contains two carbon atoms, which is ethane. Sorry. The corresponding alkane contains two carbon atoms. So to name this as a substituent, what you do, you remove the A-N-E ending of the corresponding alkane, and you replace with OXY, okay? OXY, okay? Right here.
Ethanol.
What is it?
Ethanol.
Ethanol, okay, very good. Oh, I didn't erase all of that. I shouldn't have done that. Okay, so it says ethanol. Oh, pentanol, okay. Pentanol, okay. What kind of pentanol?
3-methoxy, 1 pentanol.
Okay, where is the position of the hydroxy? 1, okay, 1 pentanol, okay. 1 pentanol, and then this here becomes your substituent that becomes 3-methoxy. One pentanol. Or you could write, you could say it's 3-methoxy penta 1-ol. You could do that also. Okay?
you not to use number one? Okay, so we have to use it.
Which one?
Number one.
Yeah, do you have to use it?
Yes.
Yes, you do have to. Because the hydroxy group could be on any of this carbon here. You have 5 carbon atoms in pentanol. So the hydroxy could be on any one of those carbons. Yes, in this case, you have to indicate the position of the hydroxy. Okay. So anyway, now we know what our ethers are. Now another special type of ether is what we call the epoxide. In this case, let me go ahead and write this. Since you cannot see the colors, okay, as if you see the green color right here. Okay, that's chlorine, right? Okay, so we have CH3, CH3, this is going away from you, and this CH3 is coming at you, and then we have the epoxide, and this hydrogen is going away from you, and this group is coming at you. Okay. Once again, you have the chlorine atom in this molecule, and you also now have the epoxy. Now, this is still an ether. It just so happens this is a cyclic ether. That is a cyclic ether. Now, the special name for this cyclic ether, we call this epoxide. The 3-member ring cyclic ether we refer to as epoxide. Okay. Now to name this, the epoxide, if you want to name the epoxide as a substituent, in this case, it becomes epoxy. We call it epoxy. If you want to use that as a substituent. Okay, so to name this molecule, therefore, what we do, we are going to name it as an alkane in which you have carbon number 1 here, 2, 3, and 4. Okay, in that case, if we are going to name this as an alkane, what would be the name? Okay, because what would be the name if the epoxy is a substituent? What would be the base name? Butane, right? Okay, very good. So that becomes 1-chloro. If don't forget, you see I have to go by alphabetical order. 1-chloro. Okay, this time you have to indicate the position of the epoxy, the oxygen atom, the carbon that the oxygen atom is attached to. So you have to now say 2, 3, 2, 3, epoxy, epoxy being a substituent, butane. Now something else is also missing here about the methyl group. Okay, where does the methyl group go? So it becomes alphabetical order, so that comes after the chloro, right? Okay, so after the epoxy. Oh, okay. Okay, epoxy, take this out. Okay, 2, 3, epoxy, methyl, right? 3, in this case, the 3-methyl, 3-methyl, and the last name, the last part of the name, butane, right? Okay. Yes. Go ahead. Oh, in this case, you don't have to show the stereochemistry because you have this carbon here. It's actually attached to the same. You have a methyl here, a methyl here, a methyl. Both of these carbons are attached to the same group. So stereochemistry here is really not important. Now, on the other hand, if you want to show the stereochemistry here, if we ask you to show the stereochemistry here, then you have to do the R and S configuration. Okay, which I don't think we want to do that at this point. Okay, because this is a chirality carbon. Okay, if you want to show the stereochemistry, you have to say whether this is R or S. You cannot say cis or trans because in relation to each one of these, you have methyl here, you have methyl here, so cis or trans is irrelevant.
What if it was ethyl instead of one of the methyl?
Or if it was the ethyl, or I mean one of these here being ethyl, then in that case, you also then have to also give the absolute configuration, because then you have the chirality center right here also. So you give the absolute configuration of this, then you give the absolute configuration of this. Okay. Okay, let us see here. Yeah, Dwayne, go ahead and read this for us.
Show the product including stereochemistry of the reaction of the epoxide below.
Okay. Thank you. Now this here is actually oxygen. I hope you can see that. It's that. Okay, I need to check that. It's actually oxygen. Okay, so let me draw it out for you. What do we have there? We have a 5-member ring. Okay, in that 5-member ring, you have the methyl is coming at you, and then you have here, right here, you have the oxygen here. And one hydrogen going away, another hydrogen coming at you. Okay, so that's what you have. Now the question is, show the product including stereochemistry of the reaction of the epoxide with this here, the sodium methoxide in the presence of methanol as a solvent. So this is what they wanted to do. That's sodium methoxide. In this case, the sodium ion is just there as a spectator ion, so you don't need to worry about that. Now, of course, the solvent is methanol. So show the product of the reaction, of this reaction with this, including stereochemistry. Now, what they are trying to test in this particular question, two things. They want to know whether you know the what would be the stereochemistry when this epoxide here reacts with a nucleophile. The methoxide will be a nucleophile, okay? And this is an SN2 type reaction. Now what you're going to find is that the epoxide this here is a very reactive species, okay? So you have CH2 here, you have CH2 here. Anytime you have a nucleophile, let us just use any kind of nucleophile. Let us say this nucleophile here could attack that carbon here, because of the fact that the epoxy is such a strained molecule. The oxygen will open up very readily. So therefore, the oxygen becomes a living group. So you could have this. The oxygen becomes a living group. And then what do you have? Okay. Now this is a typical reaction of epoxide. And the nucleophile could be just about any nucleophile. If you recall last week, Thursday, we showed you that the green here could react with the epoxide. And what does it give you? It gives you a primary alcohol with 2 carbon extension. So any nucleophile will do this. So therefore, Now, so I told you there are two things they want you to see here. The reaction of the epoxide with a nucleophile with epoxide is a way of forming ethers. In other words, this is a way of synthesizing ethers. So if you now have this, let me take this sodium out of the way. What are you going to have? You have two choices. Either this attack comes from here, or this attack comes from here. And since we say this is an SN2 reaction, okay, let me go ahead and number this. Let us say this is position 1, and this is position 2. Where do you think the attack will be? Position 1 or 2? 2. Why? That is correct. Why? Because no mechanical. Keep in mind we say this is an SN2 reaction. Yes, you right?
One is that one because
okay, it is going to be 1 because in SN2 reaction, the SN2 reaction takes place on a primary carbon or secondary carbon. Okay? Anytime you have SN2 reaction, which is essential, SN2 reaction is a nucleophilic substitution reaction. And it takes place preferably on a primary carbon or secondary carbon. In this case you have here, this will be a tertiary carbon, so the SN2 will not come here. And that is why the product you are going to get will be here. And of course, this is still here. Okay. So anytime you have a nucleophile and you have an epoxide, the epoxide is a very reactive species, and the nucleophile will react most likely, depending on the rest of the molecule, in an SN2 type reaction, in which the nucleophile will attack the less hindered, the less substituted carbon, and that is what you have in this case. Okay? Okay. Go to the next one. Okay. Let us see here. Jaconda, go ahead and read this first.
Broad structure 4 proliferate, 2 methoxy-phenol.
Okay, very good. Thank you. Okay, this is called eugenol, which is I don't know, many of you use this clove as a condiment, but that's the oil of cloves. Anyway, what they want you to do here, write the structure for this molecule. Now, before you do that, I know most of you will be asking, what is an allyl group? This here. This group here is right here. Okay, that's what we call an allyl group. Just as you have this, just as we say this is a methyl group. Okay. Okay. That is an allyl group, so you need to know that. Also, this group here, right here, this here is what we call a vinyl group. Those are all accepted IUPAC substituents. Okay? Okay, now let us come to the question. Okay, this is the molecule they want us to write the structure. Okay, taking a look at this name here. What is the base name for this structure?
Phenol.
It's a phenol. Okay, very good. I think we all know what phenols are at this point. But it's a phenol. Okay, that's a phenol. Now they said 4 allyl. Okay, so in the 4th position you have the allyl group, which is this here. The attachment is right here. Okay. And then in the 2 position you have the methoxy. Okay. So this is an ether. If you take a look at this part of the molecule, this is an ether. And this is a case in which we are using the ether function as a substituent. In this case, we now say it is a methoxy. Okay. Supposing I have this. Supposing this is what I have. Okay. And then this here. What would be the name of this compound? 4-bromo. Okay. We want to name this as a phenol, right? Okay. Say 4-bromo. True epoxy, exactly. True epoxy. That would be, in this case, you are using this group as a substituent. Okay, from propane, you remove the ALE, and then you add OXY, epoxy. Okay, so that becomes 4-bromo 2-propoxy phenol. Okay, very good. Okay, now we begin to get into synthesis. Okay, let us see here. Okay, Margaret, go ahead and read this first. Okay, very good, and thank you. Now, in this case, now we are getting into synthesis, right? Now, for you to do synthesis, what do you need to know?
Reagents.
Exactly, you need to know those reagents, you know. I bet you somebody wakes you up in your sleep, you'll be hearing my voice. You need to know those reagents, right? You need to know those reagents. Without knowing those reagents, believe me, you can't do nothing. Okay, that is, knowing those reagents is pure memorization. That is your part. Okay, so let us do the analysis here. Assuming that we know all of those reagents. Okay, now what we have there, we want to start with an alkene. Now, what this question is essentially trying to show here is show you how to make ethers, right? How to make ethers. Let me give you a little bit of a background. Okay, let us say synthesis of ethers and epoxides. Okay. Basically, we have 3 methods for making ethers and epoxides. 1, we have what we call mercuration, oxymercuration, demercuration. I'm sure you guys have heard that before. Okay. Addition, I would say addition of alcohol to alkene, to carbon-carbon double bond, okay, via oxymercuration, demercuration. Oxymercuration / demercuration. That is one method in which you can use to make alkenes. And what does that mean? In this case, we have, if we have this, we have a carbon-carbon double bond, and we have mercury acetate, trifluoroacetate. I'm sure we've used that before, remember? Okay. We used this when we were adding water. Remember when we were adding water across the carbon-carbon double bond? So in this case, you take mercury, a trifluoroacetate. Now the difference now is if you are going to add water, we will use water here as a solvent. Now the difference now, since we want to add an alcohol, let us take any alcohol. Say for example, we wanted to add ethanol. We will now have this mercury trifluoroacetate in the presence of, for example, ethanol. And then, after we do that, then we follow that always. Do you know the reagent? Sodium borohydride. This is similar to what we did for hydration of alkene to form alcohol. Okay, sodium borohydride. And once you do that, then you form this product. Okay, the clue here, think of this as a Markovnikov type addition. Think of it as a Markovnikov type addition. Okay, keep in mind what do we say we are adding? We are adding the elements of alcohol across the carbon-carbon double bond. In other words, the alkoxy, in this case ethoxy, goes to one carbon, and hydrogen goes to the other carbon. So if we say this is Markovnikov addition, let me label this. Let us say this is carbon 1 and carbon 2. Where would the hydrogen go? Where would the hydrogen go? Hydrogen goes on 1, exactly. It is a Markovnikov addition. Think of it as a Markovnikov addition of alcohol across the carbon-carbon double bond. In that case, you now end up with this. Hydrogen comes here. Don't forget, originally we do have hydrogen here initially, so this hydrogen is still here. Take this out. And so that hydrogen is still there. And then the alkoxy part of the alcohol will now come to this carbon here. Okay, so that is what we mean by addition of alcohol via mercuration, oxymercuration, demercuration. So that is one method of making ethers. In other words, adding an alcohol to a carbon-carbon double bond. Okay, that is one. Now another method for making ethers, you got this already? Okay. Another method for making ethers, let's call that number 2. Is what we call the Williamson ether synthesis. Ether synthesis. Now for the Williamson ether synthesis, essentially it is an SN2 reaction, SN2 reaction of alkoxide okay, displacing in a substitution reaction. Let us say in a substitution reaction. in a substitution reaction. Okay, what do you mean by that? Say, for example, we have this. I'm going to try to give you the almost like a mechanism for this reaction, but you don't need to know the mechanism to for subsequent problems. Okay. Supposing we have this alcohol here, and we have sodium hydride. Sodium hydride is a very powerful base. Think of it as you all know, it's an hydride. Of course, the sodium is there positively charged. Or we could use sodium hydroxide. That is also a base. Okay. Now, what do you think the sodium hydride will do first? It will pull off, abstract the proton from this alcohol, right? Okay? Abstract the proton from the alcohol, thereby releasing this pair of electrons to oxygen. Okay? So now what do we have? We now have an epoxide, right? Cyclohexyloxy group, right? Cyclohexyloxy. Find that very difficult. Okay, so we have this here. So we have this epoxide here. Now, if you now take this and you add an alkylating agent to that, when we say alkylating agent, any molecule that will allow us to form a new carbon-carbon bond, alkylating agent, right? Okay, well, we could use this, any alkylating agent. Say we use this. Keep in mind the SN2 reaction, you do require a leaving group that is attached to a primary carbon or secondary carbon. That is the requirement of the SN2 reaction. Okay, so now what do we have? We have this, come here, attack this carbon here, essentially driving this bromine away, so that bromine becomes a leaving group. Okay, and then we have this. Okay, so that reaction I've just given you is what we call, referred to as Williamson ether synthesis. It involves two steps. The first step, we form the epoxide with sodium hydride, starting with alcohol or sodium hydroxide. Once you form the epoxide, then you add any kind of alkylating agent. By that we mean any organic molecule that has a good leaving group attached to a primary carbon or secondary carbon. Okay? So for example, we could simply just do this. We simply do this. Okay, step 1, sodium hydride. And then step 2, I could add in this case I use iodide. And what will be the product? Will it be an ether? Yes. Okay, that is your classic Williamson ether synthesis. So in this case, you now have this. And what would be the name of that ether? There are two ways in which you could name it. Okay, there are two ways. Yes, go ahead. Ethyl, okay, yes, you could do that. Okay, another way to name ethers is to simply name the alkyl group that are attached to oxygen. In this case, you name the alkyl group in alphabetical order, of course. You have an ethyl group, then you have the propyl group. So you could simply say ethyl. These are separate words. Propyl. Then you add the word ether, all separate. Yeah, I know. That's what I said. Yeah. Yeah. Okay. There's another way. What other way can you name this? You could name this as an alkane, right? As an alkane, that would be ethoxy, 1-ethoxy propane, right? You could do that also. 1-ethoxy propane. Do you see that? Anyway, okay. Just to let you know that the different ways in which you could name this. Okay. Now let us come back to this problem. I've given you some background. I did say one more method to make our ethers. The other method for making ethers called that 3. Under synthesis of ether, so we now say 3. Okay. Epoxidation. Okay. Epoxidation. Okay. For epoxidation, there are two ways in which we could make epoxide. Epoxy ether. Here, if you take this, you have a carbon-carbon double bond, and then you use, have you guys heard of M-chlorocarbenzoic acid before? Right? Okay. Use this. M-chlorocarbenzoic acid. Okay, for subsequent problems, said you could simply say MCPBA, that would be fine. Okay, now if you do that, what do you get? You get an epoxide. Get an epoxide. Now another way to make epoxide, of course, is, let me take this. Got this? Okay. To use a two-step approach in which you have the same carbon-carbon double bond, you react with bromine in the presence of water. We refer to this as bromine water. We did this last semester. Now, what happens with this reagent here, it will add bromine and hydroxy group across the carbon-carbon double bond, or sometimes it could also use chlorine and water. Okay? Okay, if we use bromine water, what do we get? We get this. You notice the stereochemistry here. The bromine and the hydroxy group that are added across the carbon-carbon double bond, they are trans to each other. So you get the trans product. Now, once you get that trans product, you could now do almost like an intramolecular Williamson intersynthesis. Do you know what that means? Intramolecular. Williamson intersynthesis. What does that mean? What does exactly? If I say that I want to do an intra means that the nucleophile and the leaving group will be in the same molecule. Okay, so what do you think I am going to do now? If remember the Williamson intersynthesis, what do we do first? We form the alkoxide, right? Okay, so I could simply take hydroxide, right? Step 1. Well, let me go through the steps so you can see this better. Okay, but for subsequently you don't need to give the mechanism. Okay, so it will abstract this hydrogen here, you form alkoxide, right? Note the stereochemistry here. Okay? The oxygen and the bromine are trans to each other. So now that you form the alkoxide, what do you think will happen? Keep in mind we say intramolecular Williamson. What will happen? This oxygen now will undergo an SN, almost like an SN2 type reaction. Displacing this here. Come here. Attack that carbon from the back. Okay? And then this will leave. And then you form your epoxide. So these are the two ways in which you form epoxide. Okay? Now, so in this particular instance, therefore, supposing I just give you this. Supposing I just do this. Okay, and then I have this chlorine in the presence of water. Notice I told you that chlorine could do the same. I say that is all step 1. Step 1. And then step 2, I have hydroxide, right? And water. What will be the product? The question is, what will be the product? What do we get? Do we get epoxide? Yes. Very good. Okay, having said all of that, let us now come back to this problem. Okay? Let us now come back to the problem we are supposed to solve, right? Give you some background. Okay, now I need your help now. So what do we need to do here? starting from an alkene. Let us call this here. Let us call this compound A. Let us make the let us call this compound B. Let's do the A first. So can anybody taking a look at this? Okay, you see your ether functionality here, right? You see your ether functionality here. You see this hydroxy here. Remember I told you earlier that using the epoxy group, you could make ethers by using a nucleophile to open the epoxy, right? Okay. Keeping that in mind. So what do you think we're going to start with? Starting with an alkene. Okay, let us take a look at this carbon. See this carbon here. And this carbon here. Okay, focus on those. And of course this metal and this metal. What alkene do you think we are going to start with? We start with a carbon-carbon double bond. We already told you start with an alkene, right? Okay, you want to start with a carbon-carbon double bond? Okay. Okay, what will be on this carbon? Methyl, very good. Taking a look at your final product, you have methyl here. And also on this carbon, methyl, right? Okay, now where do we go from there? Look at what we want to form. We have the methoxy here. We also have an OH here. Think of epoxide. What do you think you are going to do first? Form an epoxide? Okay? Okay, let us form an epoxide. And what reagent do we need for that? MCPBA. Okay, so you now form okay. Now what is going to happen now? Still coming back to your final product. What do you think is going to happen now? Keep in mind that the epoxide could react with a nucleophile. Yes. Anybody has an idea what is going to happen now? Methoxide? Exactly. Okay. So now you want to take a methoxide, sodium methoxide, for example. Okay. Generally, when you do that, you do it in the presence of methanol as whatever the epoxide that you use, then you use the corresponding alcohol as a solvent. Okay. So if you do that, what do you think is going to happen? What kind of reaction are we going to get here? Substitution reaction, SN2 reaction. Because now this will now simply attack, this will come here, attack this, and this will open up. Okay? You don't need the mechanism, but I will give you the mechanism anyway, so you get this. Now this is here, and this is here. Okay? Now the methanol that is here as a solvent will simply now help to protonate this here. Come here to grab this proton here, and so we are going to regenerate the methoxide that we use. So the methoxide here is acting as a catalyst. So therefore, what do you end up getting? And that is compound A. Now the point is, for you to be able to do this, you need to know those reagents. Because when you know those reagents, sometimes the scheme will simply just come at you. But sometimes you may have to work on it. But there is some logic to it. Okay? Okay, you say, okay, you have this here. We have methoxide. We're starting with an alkene. Why doesn't this here become the carbon-carbon double bond? We'll start from there. Okay, very good. Let us now do B. B should be simple. Okay, what do we need to do with B? How do we get to B from an alkene? Notice that they did not tell you what type of alkene. You have the liberty to choose any alkene you want. Okay, so how do we get B? Anybody has an idea what kind of alkene? Okay, this is a carbon here, this is another carbon, right? Okay, carbon-carbon double bond, of course, for alkene. Will it be cis or trans? Exactly. Because the epoxidation process doesn't change the stereochemistry of the alkene. Okay, so it must use the same trans alkene. Okay. So therefore we have this. Okay, and then we use the M-chlorobenzoic acid, right? Okay, that's simple enough. Okay. Okay, very good. Let's go to the next one. Okay. Okay, area, can you see this? If you can see this from where you are sitting, way back there. Can you read it for us if you can see it? Oh, not really, okay. Okay. Ryan, go ahead. Want to attain diol? Okay. Now, what they want you to do here, they want you to use this table, but I do not want you to use that table. Let me. If I do it too fast, it disappears. Now, do not look at that table. I don't want to do it too fast because then it disappears on you. Okay. Anyway, you get the idea. Don't look at it. Don't look at it, okay? This is what they want us to do, okay? One phenyl, going from one phenyl ethanol to one phenyl 1,2-ethane diol. Okay, let us see what those look like. One phenyl ethanol, so we have ethanol. Okay, that's one phenyl ethanol, right? And they want us to go from there to here. One phenyl 1,2-ethane diol. Okay, so you see I have the phenyl there. 1, 2. Okay. Now, that's what they want us to do. Now, what this question is testing, of course, this testing your, what I would say, your knowledge of the reactions of ethers or epoxides. Reaction of epoxide, those testing your knowledge of the reaction of epoxide. Okay, so how will you do that? You want to go from this here to here. Okay? You notice the number of carbon atoms has not changed, right? Okay, so what do we need to do here? We want to form a diol. Testing your knowledge of the reactions of epoxide. Okay, that would be a clue. So what do you think we need to do? What is the first step? Starting with this here. Okay, remember how many, I gave you some steps for making epoxide or ethers, right? Starting with what? Alkene, exactly. This time not Williamson. Okay, so if you want to start with, okay, so far I gave you two basic methods for making ethers or making epoxide. Starting from alkene, or you can use Williamson's ether synthesis. So this time we agree we want to start with the carbon-carbon double bond, right? Okay, if that is what you want to do, so what does that tell us about this starting material? You have to convert this to an alkene, right? Okay, so the first thing to do is to convert an alcohol to an alkene. What reagent do we need for that? COCl3? Is that what you said? Okay, so we will take this. The reagent that will convert, in this case, an alcohol to an alkene. We could use POCl3, which is phosphorus oxychloride. Okay, you need to know these reagents. Okay, so in that case, you form a carbon-carbon double bond. POCl3, then you form do a dehydration. Okay. Now, once you form this, keep in mind this is where we want to go. Now, what will be the next thing that you want to do? As I said, this is also testing your knowledge of the reactions of ethers, epoxides. Okay, so what is the next thing you want to do? Keep in mind you want to go here. Form an epoxide, okay? You now form an epoxide, MCPPA. So now you have okay. Now, how do you now go from here to here? What reagent do you need? Water, hydroxide, and water, right? Because essentially you want to open up the epoxide. Keep in mind, we told you any nucleophile will do this. In this case, the nucleophile is hydroxide in water, okay? And what type of reaction do we call that? SN2 type reaction. Okay, attack this carbon here, then opens up. Okay? So we have, okay, do we have everything we need here? Let us see, do we have it? I will say we use phosphorus oxychloride, that is this here. So we have that, right? And then we say we need M-chloropyrbenzoic acid. We have that also right here. And then finally we say we want to use hydroxide. Do we have hydroxide? Or in this case, we could actually use dilute acid. I think they're using dilute acid here. Yeah, I think we are using dilute acid. That's what they use. Now, you could use hydroxide or dilute acid to open up your epoxide, okay? And that's what you get here. Okay, let's go to the next one. Okay, okay, now we get into mechanism problem. Mechanism problem, let me see here. Okay, we'll call on somebody back there. Everybody back there hiding. Okay, is the movie? No, no. Oh yeah, right. Can you see? Can you read this back there? No. Okay. Okay. Go ahead, Kelly.
Treatment 1,1 diphenyl 1,2 epoxy ethane with aqueous acid yield diphenyl acetaldehyde as a major product.
Okay. Thank you. Now, this is a mechanism problem. They say treatment of 1,1 diphenyl, which is this molecule here. By the way, this here, sometimes you see this, that is represent benzene. Okay? I don't think we have used that symbol before. That represents benzene, okay? Or phenyl. Okay, now, so we have 1,1 diphenyl, 1,2 epoxy ethane. Notice the name they've given us here. They are naming this molecule as an alkane. So 1,2 epoxy ethane. Now they add water to it, dilute acid. And then this is the product they got. Okay, give the mechanism for this reaction. Okay, now let us do this together. Now this is beyond knowing the reagents, right? This is beyond knowing the, now you got to actually know the chemistry now. Okay, now let's do some analysis. Look at the products. If you look at this here, this carbon here is this carbon, okay? And therefore you have to say that this carbon here is this carbon. Okay, so what is happening here? On this carbon in the product, what do you have? You have only one hydrogen attached to this carbon in the product. But if you look at this here, oh, you can see? Okay, let me write it out. This is what we have. Oxygen, okay, that is the starting material. And in the product you have this. And now here you have this. Okay, can you see it now? Okay. Now, if you look at this carbon here is this carbon. Okay? This carbon here is this carbon. If you notice, let us just put a number on it so we can say this is carbon 1 and carbon 2. If you notice in carbon 1 from the starting material, how many hydrogens are attached to it? 2. That same carbon 1 is this here, and carbon 2 is here. Now, how many hydrogens are attached to carbon 1 in the product? 1. So what does that tell you? There's going to have to be an hydride shift. In other words, there has to be some hydride shift. Okay? And to have an hydride shift, what that suggests to you, you must be forming a carbocation on this carbon next to here. So those are the kind of analysis you have to make. Okay. So if that is the case, let us see. Keep in mind, all you have is, let us now write the mechanism. You have this here, this epoxide, okay? You do have the non-bonding pair of electron on oxygen, okay? And then you have what they're giving you, dilute acid, okay? So what do you think is going to happen first? You have the proton from the hydronium from the dilute acid who protonate the oxygen, okay? So now you're going to have a protonated epoxide, right? So let us do that. So we have let us now draw our arrow. This here, keep in mind you draw your arrow from where you have electron to the positive charge, okay? Pick up the proton, and then we have this. Okay, so therefore we are going to form this intermediate. Okay, so you form that oxonium ion intermediate. Now, what do you think the next thing that is going to happen? It will break, exactly. When it breaks, where are we going to form the carbocation? The more stable carbocation, right? And the more stable carbocation will be on this carbon because it is attached to two benzene rings, right? Okay, very good. So now you have this to break. Once it does that, then you have this here. Now you have this. And then this is positively charged, right? And now we have this here. So now what happens at this point? The hydride shift, okay? The hydride. So I'm going to do this one step at a time. Keep in mind what we want to do here is to explain the product, okay? So therefore we have an hydride shift. Okay, then we have this. The hydride is now here. So now we say hydride shift. And now on this carbon here, we have now this carbon now becomes a carbocation. Okay? So keep in mind also we know that we have water is formed right here. Okay. Now this water here can now come back and grab this here. In so doing, what are we going to get? We now have formicarbonyl. Okay, that water comes in. Let me just put the water here. And so once the water comes to grab that proton, we now regenerate the original hydronium ion. So the hydronium ion here is only acting as a catalyst, and therefore you then form your final product. Like I said, this is beyond knowing the reagent, but before you could do this, you need to know your reagents. Okay? At this point, you then have to think, use some kind of logic to critical thinking to work this out. Okay, the hydrogen is here, and now you have this, plus your hydronium ion. Okay? Okay, so that is, keep in mind for mechanism problems, you really have to see beyond just the reagents. Of course, before you can do the mechanism, you need to also know your reagents. Let's do one more problem before we go. Oh, okay. Okay, so when we come back, we are going to finish up on chapter 18, and then we will start with chapter 19. So before you come, okay, of course tomorrow, don't forget tomorrow, we have the online session tomorrow on chapter 18. We continue with the hour problems. And then before you come in on Thursday, please go ahead and read the webcast on the previous chapter 19 lectures. Those are already posted in Blackboard, okay? I just read the first 2 lectures, okay, from chapter 19. I think I have about 5 lectures. I also want to warn you, the next exam is almost 2 weeks from now, which is March 5, okay? The next exam is on March 5, and to cover chapters 17, 18, and 19. At this point, we have almost finished chapter 18, okay? On Thursday, we start with chapter 19. Okay, so see you on Thursday.